Here's another video of the lecture Intro PDE. In this video we present section 4.3. So this is the mean value property. So we transfer another tool which we already have seen for the Laplace equation to the heat equation. It will become more complicated. Especially we have to choose the ball properly. Yeah, this is the so-called heat ball. Yeah, also we define the heat ball. Heat ball. This is a subset over of n cross r. And it's defined here by this formula. So we use the fundamental solution to define the heat ball. Yeah, we could also have done this by in the Laplace equation. Yeah, if you remember that for the Laplace equation, the fundamental solution is just the power of the length. An inverse power of the length. Yeah, one gets a similar description of the round balls if we make such a bound. Yeah, with the power of r is different, but everything else is very, very similar. So if we do the same thing for the fundamental solution of the Laplace equation, we get usual balls, and which are the balls which we used in the Laplace equation. Yeah, so this is really a natural way to generalize this to the heat equation. Now let's analyze or describe this set here. Yeah, this set. Okay, this is the fundamental solution, and besides this factor, this is also the fundamental solution. Maybe I write it, x minus y, t minus s, how this looks like. This is this inverse factor, so it's 1 divided by 4 pi over n half, and then t minus s over n half, and then times this exponential of minus x minus y, absolute value squared, divided by 4 times t minus s. And here we typically assume that this is positive. Yeah? T minus s should be at larger or equal to 0. So this means, of course, that s is smaller than t. So the times in the heat ball, they are always smaller than t. Yeah, here we have written this extra. Okay, so this is the inequality here, and now we here in this step we just rewrote everything. Here's the power of n half, and from the left hand side to the right hand side, we took the inverse and collected this to 1 power. So we get this expression here, and and took the inverse. Here the n half of the 4 we also included here to this expression. Okay, and then we take the logarithm. Yeah, we take the logarithm of this whole expression. Since everything shows up with a power of n half, we get in front an n half, here this is the logarithm of r squared, is 2 times logarithm of r minus logarithm of this expression, and minus logarithm of pi by this factor. Okay, so all together then we get here this. Now in the remaining, we multiplied this to the left hand side, and then the 4 cancels with the 2, so it remains a 2. So we have this expression. Now let's draw this heat ball. Yeah, we know that S is smaller than T. Yeah, we know S is smaller than T. So T minus S is larger or equal to 0. If in the limit that S goes to T, from below, if F goes to T, where does this function go to? Also for R is of course given, this is some constant, but limit, if T minus S goes to 0, T minus S going to 0 of T minus S times logarithm of, and here we have in front of things, a logarithm is of course for small values negative. This goes to 0. So the right hand side really goes to 0 for very small if S goes to 0. So this means for S going from below to T, small, also approximately S, we have that x minus y also goes to 0. Okay, now we increase, if this T minus S increases, then at some point here this turns this factor here is positive now, but at some point T minus S becomes larger than 1, and then ln T minus S becomes positive. So for S much smaller than T, ln of T minus S becomes large, and this means that the right hand side here and the right hand side becomes negative. So there's no solution anymore. So no points in this ball. Okay, so how this ball looks like, let me draw a picture. If we draw here coordinate x and here coordinate t, let's say we have here a t, then the s, and we have here our x. Then for s equals t, this is 0. And then for smaller values, here is also where it becomes 0. And in between it becomes larger. So, and then it's of course rotational invariant around an axis Yeah, also in higher dimension, it's rotational invariant. This is a rotation axis. Okay, so it's like a ball, but in the past, yeah, all times, all s are smaller than t. Yeah, okay, so this means it's strictly in the past. Yeah, also this only point contains the same time. Okay, this is how this ball looks like. And now we have a very similar property like the mean value property of Laplace equation. Okay, the statement is more complicated, yeah, because we have this complicated heat ball and we have here another weight function. It's not just the integral, but we have a weight function. And here we divide by the corresponding function if u is equal to 0. Yeah? So here, this really gives a mean in the sense that this is the integral, this is this integral for u equals 0. Yeah? This we will see. Okay. Now let's prove this theorem. Yeah, let's prove this mean value property. Okay, the proof is more or less follows the same idea. Yeah, we also define, again, we define this function phi of r, and then try to calculate the derivative with respect to r. First, in order to calculate the derivative with respect to r, we should make everything independent, the domain independent of r. Yeah, and we have, also we clearly have that the map, also first of all, if we look for phi, and if we multiply the arguments, yeah, sorry, with a constant s, let's say, yeah. So if we with a constant r. So if we multiply r and r squared t. Now let's go back where we have seen this function. Yeah, we introduced this function. Here it is. Yeah, here it is the definition. Yeah, then you see this term here. This is independent of r. Yeah, because in the top we have r squared and in the bottom we have r squared, so this cancels. So this is completely independent. The only dependence on r is here. And what we get 1 over n over half, but r squared, so 1 over r to the power of n of phi of x t. Yeah, so we have this scaling behavior. Yeah, this scaling behavior. Now this is exactly the power which we use to define the heat ball. Yeah, and as it should be, of course. And now we look for the map. Yeah, y t maps to ry r squared t. I claim this maps the t ball around x t 1 to the heat ball, sorry, the heat ball to the heat ball x rx r squared t comma r. Yeah, and this follows from this formula and this definition. Yeah, you see here this 1 over power of Rn. We exactly get this factor here. Yeah, so if we insert this, then and if we write this here, this expression to be larger than, we want that this, if x and t obey this equation, yeah, then we have 1 over Rn, yeah, and then if we now insert, no, sorry, yeah, if we write phi of xt, no, sorry, yes, if phi of xt larger or equal to 1, yeah, this is equivalent by this formula that phi of Rx r squared t is larger or equal to 1 over Rn. Yeah, so we see indeed that this map here, if y and t here belongs to this element, yeah, then we see this belongs to this element. Yeah, okay, yeah, we should, here one should insert, here's missing, of course, the x. Yeah, okay, and this explains this relation here. Yeah, so we indeed have this relation, and this means now we use this new coordinates. Yeah, so we first transform this. We write this expression here first without this constant Cn. Yeah, we don't take here this constant, but this is completely this expression. Now we just replace y by ry, s by r square s, and then we have this formula. Yeah, okay. This is just a replacement of variables. We just rename the variables. So this is clear. This is the same. But now we know that this map here maps this ball to this ball. So the coordinates y and s belong to this ball. Yeah, so we now integrate over this ball and take these variables. And if you see the powers, here we have an r to the power of n, here we have an r to the power of 2, so this means n plus 2. Here we have an r square, here we have an r fourth. So it remains an power of Rn. This cancels with 1 over Rn, so we really get this expression. Yeah, here Rn, r square, r to the power of 4th, all together. This gives an Rn and cancels with this, and we get this expression here. So now we want to take the derivative. Yeah, okay, let's see here. From this function here, now we take the derivative. Here, finally, here we have, the domain is now independent of R. So it's quite easy to calculate derivative. Yes, let's do the calculation. Yeah, if we calculate d by dr of u of ry and r square s, what we get? Here we get, of course, the gradient. The inner derivative is y, so we get y times gradient u of ry, r square s. And here we get a plus 2rs u dot of, again, ry r square s. Okay, these two expressions. We just insert these two expressions and write this here. And now, so this is derivative. And now we transform back. Now we want to go back to to the ball with radius r. Since here we have an additional y, we get 1 power more. Yeah, we get 1 power more. You should keep in mind that this y here is this y divided by this is r times y. Yeah, so we get 1 power more due to this y. Yeah, because here we have an extra power of r in this y. So we get here this, and on this side we have this s, with cancels with the s square, so we only get this term, but s has 2 powers of r. Here's 1 power of r, so again we also get 1 power cancels. Yeah, so we have, compared with the r to the power of n, which we had here, we get here also one higher power of n. Yeah, from here we have 2 powers, but from here we have 1 power. So here we have 2 powers more in the bottom term, and here we have 1 power less. So we get this. Now we define a function which describes us this ball, and this function is defined just in the way that it's the ball is the points where this function is positive. Yeah, recall the function is just this expression here. Yeah, this is okay, together with this expression. Yeah, so we rewrite this equation as a function. Yeah, so we put this to the other side, and then we have exactly, if we rewrite this inequality, you should keep in mind that here in our situation x is 0 by translation. Yeah, okay, I forgot to mention it. Of course, the heat equation is translation invariant, so we may shift everything to the origin, so we set x and t equal to 0. So then x is 0 and t is 0. Yeah, so all this term simplifies, and then we have here y square, and we take this and then bring this to the other side, and then we have exactly that this function is positive. So this is by definition chosen in such a way that this ball is defined by this property. Now this has the nice feature that this function vanishes at the boundary. Okay, now we have these 2 terms, and now we only calculate the second term. Yeah, now we calculate the second term. This is the second term, and what we have done from here to here, we just observe that we might write this term as the gradient of psi, y times the gradient. Yeah, because the only thing which depends on y is this expression, and this expression, if we take from this the gradient, this is of course y divided by 2y divided by 4s. So it's 1/2 of y divided by s times y is y squared divided. So since it's 1/2, instead of 2 we get a 4. So this is just this expression. Now we have a gradient here. Yeah, now we have a gradient. Now we can do partial integration. Yeah, so this means this gradient we move to this side. Yeah, and if we calculate the gradient of this, then we get 2 terms. The gradient of y gradient y is of course n. Yeah, because dy1 derivative, the derivative of y1 with respect to y1 is of course 1, and the same for all. If we take the sum, we obtain n. So gradient of y is n, so we get this term, and with a minus by partial integration. And we also need to take here this term. Yeah, these are the two terms. Okay, this is just partial integration. Remember, y vanishes at the boundary of this ball, so we get no boundary terms. Yeah, very important. No boundary terms because psi vanishes at the boundary. Now what do we do here? Here we have done another partial integration. Also this is unchanged. Here this minus goes here. But here we have done another partial integration. This time with the integral with respect to s. Yeah, so since here we have a derivative, we move this derivative to the psi, yeah, by partial integration. Yeah, this is now just partial integration for one variable, just for the real variable ds. Again, we use that at the boundary. This vanishes, so we get no boundary terms. Yeah, and by partial integration, this minus goes away, so we have only here this minus and this expression. So this was another partial integration. Now what we do in the next step here, in the next step, also this step I explain now from here to here. Okay, what we do, we just calculate the derivative of psi with respect to s. Yeah, here we get minus y squared over 4s squared, yeah, with a minus sign. And here, this expression, we get a minus n half times 1 over s. Yeah, this minus, also since the logarithm of a factor, yeah, this minus and this 4 pi, this cancels, yeah, because the logarithm of a product is the sum of the logarithms. By taking the derivative, this doesn't contribute. So we just get minus n half times 1 over s. So this is this expression here. This we keep. Yeah, and yeah, this we keep. Okay, and so we altogether get this expression. So we just inserted psi dot. Now what we do now? Now we insert this whole term again here. And then we have the nice thing that here this 4 with this 4 cancels. But here we have a minus. So this term now cancels with this term. Yeah? Here this is completely the same. So we insert this integral here, and then this cancels with this term. And what remains? It remains this term. Here we used the heat equation. Yeah? U is a solution of the heat equation. So U dot is the same as Laplace U. Yeah? So U dot is the same as Laplace U. Okay, so this is this expression. This term cancels here with this, and so it remains this expression. So we only have these two expressions. Now we are almost done. Now we only do one more partial integration, and only with this term. Yeah, this term, Laplacian, is of course divergence of gradient. So, and the gradient we do a partial integration, and then we get rid of the minus, and the gradient now acts on the psi. So we get this expression. Now here we insert the gradient of psi. Yeah, the gradient of psi, we already did this once. Yeah, then we have, this is y times y times 2s. Yeah, because by the factor 2 we get 1 cancels with the 4, so we have y times y divided by 2s. Yeah, and so we have this expression here, and here's the n, and then we see that this really cancels. Yeah, this is 0, and so everything is 0. So we have proven that phi prime is 0. Yeah, this is this long calculation. Of course, it was much more complicated than in the Laplace equation, but the main ideas are completely the same. And now it's quite easy to finish the argument. Yeah, by continuity, also if we make the ball very small, and if the radius goes to 0, then the ball becomes very small. Yeah, so if we make the ball very small, in the limit r going to 0, then by continuity, in this integral here, in this integral, we may replace u by the constant value at 0. Yeah, also the difference is, also since this is positive, yeah, if we subtract from u the value at 0, 0, yeah, then this becomes very small, and then it remains to calculate this integral. Yeah, but this integral now, yeah, so we get constant, so u of 0, 0 times this integral. But this integral here, again, we may do the same trick, transform the coordinates. Also here we just replace the coordinates by, we replace y by ry and s by s square s, and do the same here. And then we remember that this map, that if ry and rs ranges over this is equivalent to that y and s ranges runs through this ball. And here this factors, yeah, the powers of r. Here we have an rn, here we have an r square, here we have an r square, here we have an r fourth. All together we get an rn, this cancels with this, so we get this. So this is indeed our constant. And so by continuity, we had this argument several times, so I don't repeat it here. Yeah, you just should here subtract, also this whole, if we insert a constant, yeah, then if this is constant, then we just get this integral which we calculated, which we called Cn. So if we subtract from this integral Cn from this integral, Cn times u of 0, 0, then in the limit r going to 0, it goes to 0, because this converges to u of 0, 0, yeah, and everything is positive. So we really obtain that in the limit r going to 0, this goes to this constant times u of 0, 0. And this clearly proves the statement, yeah, because we have shown this is independent of r, like in the mean value for the Laplace equation. In the limit r going to 0, it goes to Cn of u0, 0. So if we divide this integral by Cn, we really get u of 0, 0. Okay, and by translation, we get really this formula. So we have proven the mean value formula. One can explicitly calculate this constant. Yeah, let us show you how one can calculate this. Okay, this ball here is just defined by this inequality. Yeah, this is nothing else than written down this inequality. Yeah, for x equals 0 and t equals 0. Yeah, then we only have here minus 2ns, and here r equals 1, so this is 0, and this is minus ln of minus s minus ln 4 pi. So you see this is really exactly this inequality. And the right hand side gives this inequality. Yeah, so y squared smaller or equal to this. Now clearly y squared is positive or non-negative, more precisely. So this means the right hand side has to be non-negative. Yeah? Okay, since the integral, also the boundary terms don't contribute, we insert here the strict inequality, because for s equals 0 we have problems. Okay, so we see, also we can by the integration, yeah, the set where this is 0 is clearly a set of measure 0, so we can restrict to the points where y squared is really positive. And this is then, by this inequality, means this has to be positive, and this means this has to be smaller than 1. So this means s, yeah, so this means s lies in is smaller than 0 and larger than minus 1 over 4 pi. Now, of course, by definition, yeah, this ball here for t equals 0, s is non-positive, yeah, and okay, and we omit the part where s is 0, so we get this. Now we insert this, so this means we have to integrate y squared over, and here 1 over s squared, and then we integrate y squared over this ball. This ball is exactly the radius, yeah, over this ball. In the inequality we had this ball, with this is exactly the square root of this expression here, yeah, because y squared is smaller than this. So we really immediately get this expression now. Okay, now we use polar coordinates. Then we know, of course, the ball has volume n times omega n times power of r to the power of n minus 1. But here we have another factor of the square of the length, so we get an additional factor r squared. Yeah, if we integrate this over this ball, an additional factor r squared. And then we should integrate r to the boundary of this ball, yeah, by polar coordinates, and then we should integrate s. Now now we substitute, yeah, we want to get rid of this negative s, so we replace s by minus s, yeah, and then of course, and we interchange the boundaries, so the negative of the s is cancelled by the interchange of these boundaries. Yeah, so we get then this expression here. Look, we get here a minus, but here the minus goes away. Yeah, but this is of smaller than 1, so the logarithm is minus, so the whole thing is positive, so this works. Okay, now we can calculate. Now we integrate. Yeah? Now we integrate this integral over dr. We can of course integrate, yeah, the antiderivative is of course r to the power of n plus 2 divided by n plus 2. The n omega n we put outside. Here the first integral we call, and then we insert this boundary, and then we get this expression. Yeah, and then we insert this. Okay, we get n omega n. Now we should insert this for r. Yeah, here we have several powers of s and powers of n. Let's first look at the powers of n. We have here 2n and of course the power n plus 2, but since it's the square root, half. So this is this 2n, n plus 2 half. Yeah, this is here this 2n. Then we have an s, also n plus 2 half, this s, and then we also have this logarithm, 1 over 4 pi s to the n plus 2 over 2. So these are these factors, and yeah, the n plus 2 we put outside. So here we just inserted this. Now we should integrate over ds over s squared. And now we make a substitution. Yeah, what do we substitute? Now we substitute in this integral. We substitute, as instead of s, we now take a variable t as an integration variable. Yeah, but since here we have this logarithm, we put this 4 pi s as the logarithm of this expression. Yeah, so 4 pi s should be this expression. Yeah, this means logarithm of 4 pi s is then now minus 2 over nt squared. Then logarithm of the negative is of course the minus, so it's 2 over n times t squared. So the logarithm now has the form 2 over n times t squared. 4 pi s has this form, and the derivative, now if we take here, of course we may write this as up to factor 4 pi, but this doesn't contribute for this quotient. So if we take the logarithm, yeah, logarithm 4 pi s is equal to minus 2n over t squared. And if we take the derivative here of this, then we have 4 over nt dt. And the derivative of this is of course this thing, yeah? Yeah, because it's 1 over, we have a minus, yeah? Okay. So we have this expression. Now we insert everything. So we replace the s by this factor over 4 pi. So s is of course e to this power over 4 pi. Yeah, this is s here over n half. Okay, y over n half. Here we have ds over s. This we get by the dt. And so one s cancels. Here we have s to the power n half plus 1. Yeah, this n plus 2 over 2 is of course n half plus 1. But this 1 cancels with 1 power of s, and the other one here we have here. Yeah, so we only have n half. So we have this n half. So these are all the ds besides the dt's. Then we have this term here, 1 over logarithm of this term. This is of course 2 over n times t squared. 2 over n times t squared to the power of n over n plus 2 over 2. And then we have here finally this term here. We have 4 over n times t dt. This is this measure. And what is with the minus here? With the minus, we should keep that 4 pi s. Yeah, and 4 pi s is of course here it's at this boundary it is exactly 1 4 pi s. So this means this factor here is at the upper boundary 0. So this upper boundary corresponds to this 0, and this lower boundary, yeah, then t has to go to infinity in order that this goes to 0. So this is infinity. So we again replaced the order, also the upper bound and the lower bound, and this cancels with this minus. So then we have this integral. Now this integral is this integral, and yeah, here these factors just remain. Now we have, of course, lots of powers of 2 and powers of n. Yeah, here we have let's see with the powers of n and the powers of 2. Okay, we first this n, omega n, we keep, and then this. Okay, now let's look at the powers of 2. There we have here 2 times n plus 2 over 2. But here we have another one, n plus 2 over 2. So this means altogether this, with this we have n plus 2. But here we also have an 4, but now in the bottom over n half, this is also 2 over n half. Sorry, 2 to the power of n. So here this is minus n. This comes here from this 4. And finally here we have this 4. This is 2 times 2. So we get one factor 2 here, and another factor we write here. So these are the powers of 2. Now what is with the powers of n? Here we have n to the power n plus 2 over 2. Here we have n to the powers n plus 2 over 2, but in the bottom. So this cancels with this n. And so this n remains, all other n's go away. Now here the pi, we have n pi to the power of n over half. This we have written here. So these are all factors. Now what are the factors over the t? How many t's we have? We have here 1t. Then we have here t to the power of n plus 2 over 2 half t squared. So this is t to the power n plus 2 and t. This is t to the power n plus 3. So, and here we have n plus 2 and 1t we put here. So this is indeed t to the power of n plus 3. So now we have all powers of t, and so we see we really get this factor here. So we completely get this factor. Now we have written this because then we can do a partial integration. Yeah? This here is up to a minus the integral of the antiderivative of e to the minus t squared. Yeah, so this is the antiderivative of t e to the e to the minus t squared. Okay, sorry, here's a minus. Let me call missing. Okay, now I have corrected the minus. So the derivative of this function is this function here. E 2t times e minus t square. This is up to and minus the antiderivative of e minus t square. Yeah, so by partial integration, we calculate here this factor here. This is 2 to the power of 3. This is 8. The n cancels with the n here, so 8 omega n, n plus 2, and p over n half. So with a minus, yeah, the antiderivative here is we get a minus of this function, and then times this. And by partial integration, we should subtract the derivative of t to the power of n plus 2, which is of course n plus 2 times t to the power of n plus 1. With a minus we get now a plus, and then the n plus 2 cancels with this n plus 2, so we only have this factor, and then it remains t to the power of n plus 1. So we get this. Yeah, this expression here. Now we again put here in the factor 2t. 2 times 4 is 8, so this is this factor, and here t to the power n. Now we do another partial integration, yeah, because this is again the derivative of minus e to the power of t squared. So we get this. And then we should take the derivative of this. So then we get back an n. Now again with a plus, n omega n, for this factor remains, and e to the power exponential of minus t squared, of course, and tn minus 1. Yeah, since we have taken the derivative, we get an extra factor n. And now look at this. This is now very nice, because this is just the integral, also this is in polar coordinates, the integral of e to the power, e exponential of minus x squared, yeah, on Rn. This is by polar coordinates, of course, exponential of minus y squared on the Rn, and this is of course the same as this product here, but we already know that any of this factor is p is the square root of p, so this cancels with this, and we just have 4. So this shows that this factor is in Cn is indeed 4. Yeah, in particular, this shows that this factor is finite. This is maybe the only thing which we all really needed in this proof. So this finishes this section on the mean value for the heat equation. So let's recall what we have done. We proved the mean value theorem for the heat equation. We first defined the heat ball by using the fundamental solution, and then we did some calculation, and then we stated the mean value property for the heat equation. It's quite more complicated, yeah, because we have to integrate over the heat ball, yeah, which is a ball poorly in the past and which is more complicated. And we have some weight function. Okay, and then this is the statement with some constant, which finally we showed that this constant is independent of the dimension and is always 4. And then we did the proof, and the proof was very similar. In principle, it was completely analogous to the proof for the Laplace equation. Okay. Thank you.